In the previous sections, we were working on calculating electrostatic force, and we're going to move from there to using that force to calculating an electric field. Now, you've got three equations that you're going to be using, and I want to make sure that you understand the difference between these equations. This first one is Coulomb's law, which we've already been using quite a bit. F equals K times Q1 times Q2 over R squared. This equation is being used to calculate the electrostatic force between two charged objects. And we have said before that we don't use the sign of the charge when we're using this particular equation. And again, the reason is because let's assume that I have a positive charge here and I have a negative charge here, so the Q1 and Q2, and obviously there's a distance between them. When I calculate the force, the direction of that force is going to depend on which of these two charges I'm talking about. So if I'm talking about this charge and I have a negative, obviously opposites are going to attract, so the force is going to be going off to your right for this particular charge. But for the negative charge, it's going to be drawn towards the positive charge. So if I'm focusing on this charge, the force is going to be off to my left. So it depends on which charge I'm focusing on as to which direction the force is going to be. And so a positive or a negative sign isn't going to help me determine any kind of direction of force because it depends which one I'm focusing on. So when I'm using this particular equation, I'm not using the sign of the charge. I'm only using the magnitude of the charge. Okay, now in this section, we are now introducing two equations for the electric field. And electric field, you've already gotten some practice drawing some field lines for that, and you can see what happens with an electric field. And remember that we're always drawing an electric field assuming that you're going to drop a positive test charge in there and then determine which way that positive charge would end up moving, assuming that your field is being created by stationary charges. You drop in a moving charge and then which direction is it going to go. So in this equation, E equals F over Q naught. The electric field is E, and F is the force that's experienced by a positive test charge. And so, therefore, if you calculate this field and plug it in here, you need to put either a positive or negative sign on it, depending on direction, as if you had dropped a positive test charge in there. Because you're going to make this a vector quantity by putting a sign on it, you're also going to include the sign for your test charge as to whether it's positive or negative. Because we know that electric field lines are assuming a positive test charge, and so if it would happen to be a negative test charge, then it's going to pull that field the other direction. So we're going to include signs for both the force and the test charge if you use this particular equation. Because what this equation does is it gives us the instantaneous electric field, and again, it's instantaneous because this charge is moving, and so as soon as it moves, the force is going to be different because the distance is different. So this is for an instantaneous electric field as experienced by a test charge. Now, this other equation, same E, but this one is K capital Q over R squared. So this little q is the test charge, and it's going to be movable, but this big Q is a stationary charge, and it's the one that's doing the creating of the field. So again, this is the electric field that's being produced by a stationary charge. And I'm going to be able to calculate that electric field at some distance from that stationary charge Q. Once again, I'm not going to be able to tell anything by a sign here because I don't know for sure if I'm dropping in a positive test charge or if I'm dropping in a negative one. And so that has to be determined once you know something about the test charge. So down here, I'm not going to use the sign of the charge. So Coulomb's law and this equation for electric field, I'm not using the sign of the charge, but this one I am using the sign of the charge. So you want to try to make sure that you can keep all that straight in your head. Okay, we're going to look at example 13.4 and go through that one together. It says, consider the two stationary charges given in the previous example, a negative 0.3 and a positive 0.6 coulombs. if these two charges are 1.60 meters apart, what are the magnitude and direction of the electric field at a point halfway in between the two? So obviously if they're 1.60 meters apart, the halfway point is at a 0.80 meter distance from each one of the charges. So if I'm asked to calculate the electric field at this particular point right here, which one of these equations should I use? Well, I'm calculating the field at this particular point. They didn't tell me anything about a test charge, so if I don't know anything about a test charge, this equation isn't going to do me any good. I'm going to have to use this one instead because this point, both of these charges are stationary, and so I'm going to be able to calculate the electric field at some certain point away from these stationary charges. So similar to what I had to do before, I'm going to calculate this electric field based on each one of the charges individually, and then I'll have to sum them up together. So I'm going to start with this positive test charge, and I'm going to use KQ over R squared. K, capital Q, I should specify, KQ over R squared. And so K is the same K that we've been using all along, 9.0 times 10 to the 9th Newton meters squared over Coulomb squared. The stationary charge creating the field is a 0.60 coulombs. And the distance is 0.80 meters from the point in space that I'm talking about, okay? So when I do this math and chug all those numbers out, I end up with 8.4 times 10 to the 9th newtons per coulomb. Okay, how did I get that? Well, what happens is that this meter squared and this meter squared cancels out, and this coulomb and one of these coulombs cancels out. So that gives me newtons per coulomb. So what that's telling you is that an electric field produces a certain number of newtons of force for every coulomb of charge that's present in the field. Okay, so now I need to start thinking about direction here again, just like I did before. So if I have this electric field exerted by this, I have to assume that when I'm determining the direction of the field that I've dropped in a positive charge. So if this is a positive and this is a positive, these two are going to repel each other. And so if they're repelling each other, the electric field is going to have a force that's going this direction at this particular point. So this is going to be 8.4 times 10 to the 9th newtons per coulomb, pointing off to the right. Now I need to do exactly the same thing for the negative charge and figure out the electric field from that one. So that one is going to be E equals K times the test charge, which is 0.30 coulombs. And again, I'm not using the sign because I don't know for sure what that test charge is going to look like. There isn't even one there right now. Times 0.80, whoops, forgot my units. 0.80 meters squared. And so when I chug those numbers out, that's going to give me a 4.2 times 10 to the 9th newtons per coulomb. Okay, so now let's look at this one. So the electric field caused by this one, if I drop in a positive test charge at this point, positive and negative, those are going to attract each other. So that means this one is also going to be going off to the right, 4.2 times 10 to the 9th newtons per coulomb. I just drew arrows there indicating direction. I did not try to make them vectors and try to get them the right size, so I don't want you to think that, that they're about the same size. Actually, the green one should be about half of the length of the red one had I drawn them according to the right size. So now that I have that, I can calculate the total electric field by adding the two of them together. Convention says that vectors to the right are positive and to the left are negative, so both of these would be positive. So all I have to do is take 8.4 times 10 to the 9th plus 4.2 times 10 to the 9th, and that should be newtons per coulomb. And so when I add those together, I'm going to come up with a final answer of 1.26 times 10 to the 10th newtons per coulomb to the right. Okay, so there's our answer for the first part of the problem. So again, you can see that it's very similar to the problems that we did when we were calculating force between two charged objects. I've picked this point. I've calculated the electric field due to this charge, calculated the electric field due to this charge, and then added the two vectors together. Okay, so that takes care of the first part of the problem. Then the second part of the problem tells you, suppose a negative 0.006 millicoulomb charge is placed directly between the two stationary charges. So basically what we're saying is, now in place of just a point here, now I'm actually going to make that a charge instead, and it's going to be negative 0.006 millicoulombs. Okay, so it's a charge now in place of just this point in space. And so then it wants to know what is the instantaneous electrostatic force it would experience. Well, now that I know something about the test charge, I know the magnitude and I know the sign of the charge, now I can go back and I can use this equation to figure out the electric field experienced by this particular charge. So, I'm going to separate this off here. So now what I'm going to use is this E equals F over Q naught. I've already calculated the force as, I'm sorry, I actually haven't calculated the force. Force is what I'm trying to find. So the E is what I've already calculated. So that's 1.26 times 10 to the 10th newtons per coulomb. Okay, and that's positive because it's off to the right. The force is what I'm trying to find, and the magnitude of the test charge is a negative 0.006 millicoulombs. So what that actually is, I've got to change it to coulombs. So that's going to be a negative 6.0 times 10 to the negative 6 coulombs when I do the conversion. I'm going to assume that you know how to do that. Okay, so I now have this equation, and so when I solve this, my force obviously is going to come up negative, so I'm going to have a force that is negative 7.6 times 10 to the 4th newtons. What's that negative sign mean? It means direction, and so then my final answer is going to be 7.6 times 10 to the 4th newtons to the left. Okay, so there's the answer to the second part of the problem. Okay, so just one more time, this is when you know something about the test charge. This one is when you don't know anything about the test charge. You're assuming a positive test charge to calculate it. This one you're going to use signs. This one you're not going to use the signs. Okay, so you can get some practice doing problems with that today.